In this lecture, we'll talk about General Purpose I/O, or GPIO. So General Purpose I/O pins are pins that we can either write to a logic 0 or 1 or read the 0 or 1 from the pin. So some examples of things controlled by GPIOs could be LEDs that you turn on or off, switches where you read the value high or low, or connections to other things like digital logic, other chips. In general, as you are trying to get your head around GPIO for a new microcontroller, first thing to do is look at how many GPIO pins the microcontroller has and how they're named. Each pin generally can be configured either as an input or an output or some other special function, say a serial port or a data converter. So you need to figure out how to do that configuration, and then you read or write the pin. So on the FE310 board, there's one GPIO port, GPIO 0, that has 32 bits associated with it. However, our chip doesn't have enough pins to bring out all 32 GPIOs, so only 19 of them are accessible. And on this picture, we see the mapping. Here's pin 0, pin 1, pin 2, pin 3, pin 4, pin 5, and so on. Some of the GPIO pins have multiple functions. For example, pin 3 through 5 are also associated with a serial peripheral interface, and we can either use them as regular GPIO or as SPI. There's a blue LED on the board that's connected to GPIO 5, so when you drive that pin high, the LED turns on. When you drive it low, the LED turns off. And if the serial clock, S clock, is pulsing because you're doing serial transmission, you'll also see the light pulse. So the numbering on these pins is very small, and unless you have very good eyes or a magnifying glass, you may not be able to actually read it very well from the silk screen of the board. So this page is a pretty handy one to refer back to that shows which pins are which. They're also labeled on the back of the board, but that doesn't help you very much if you've plugged the board into your breadboard. The GPIOs are controlled by memory mapped I/O, and you may recall that the base address for the GPIOs was address 1001-2000. There are a bunch of registers starting at that address. Each register is 32 bits wide and has 32 individual bit fields to control the 32 different GPIOs. So 32 bits is 4 bytes, so each register is 4 bytes past the previous one. And the first 4 registers are input value, input enable, and output value. Then there are some registers related to controlling an internal pull-up, setting the drive strength of the pin, a whole bunch involving interrupts, and 2 of them for I/O special function registers to enable or select a special function register that we'll talk about later. So on reset, 3 of these registers are all initialized to 0 to disable all the GPIO pins, so they don't act as input, output, or have an internal pull-up. And that way, the chip won't do anything funny after reset. So let's say we wanted to write some code. In the previous example, we didn't talk about the enables yet. So now let's introduce the red lines of code to provide the enables. So the input value register was at 1001-2000 plus an offset of 0. That's this. The input enable register is an offset of 4. So that's the same base address plus the offset of 4. The output enable at an offset of 8, and the output value offset of C. So we've got pointers to all the registers. Let's write a 1 to bit 19 of the input enable register to make input 19, GPIO 19 be an input, and we'll make GPIO 5 be an output. Then just like we've done before, we could read and write the bits. We could read the value of GPIO 19 by looking at all 32 values in the input value register, shift right by 19, and then AND with a 1 to get just bit 19. To do the same thing to look at the value and then wait for that value to be 1. So while it's not 1, we'll wait and then it becomes 1. If we want to write a 1 to GPIO bit 5, we OR that bit with a 1 in column 5. Here, to make that would also turn on the blue LED. If we AND with a 1 in every column except 5, then we turn off the LED. You need to be a little bit careful if you're using the Red 5 red board instead of the Thing Plus, because the numbering on the board is different than the numbering of the GPIOs. It's Arduino style, but it's pretty confusing if you're writing programs with respect to the GPIO numbers. So the pin named 0 is actually GPIO 16, the pin named 1 is GPIO 17, and so on. Pin named 8 is GPIO 0. Let's take a look at an example. So suppose we had a switch and an LED, and we wanted to write a program that would read the value on the switch and hooked up to GPIO 19 and write that value to the LED on GPIO 5. This is a little bit silly because we could have done the whole thing with a wire instead of a $30 microcontroller board, but what the heck. So we again declare our pointers to the 4 registers. We need to enable the registers, so we make pin 19 an input, pin 5 an output, and then we can have a loop where we read the value on pin 19 using our idiom to read a pin value, and if that value is true, then we turn on pin 5, otherwise we turn off pin 5, and we repeat indefinitely. So most GPIO pins are also associated with other special functions. For instance, our microcontroller has serial ports, several types, and pulse width modulation signals. So, for example, GPIO pin 2 can also be used as a chip select for a serial peripheral interface, or as a pulse width modulation output. Pin 3 is a data signal for the serial peripheral interface, or another pulse width. Pin 5 is a clock for the serial peripheral interface, no other options. So if we want to use a pin as a special function, we use the IO function enable, set that to 1 to use special functions instead of GPIO. And then we use the IO F select to pick which function we want. So for example, if we wanted to make pin 13 be a pulse width modulation, we would write bit 13 of the IO F enable to be 1 to enable special functions, and we'd set IO F select to be 0 if we wanted to use it for I squared C. We'd make it 1 if we wanted to use it for a pulse width modulation.